All right, today, or in this video, we're going to talk about the hydrostatic pressure. Pressure in a fluid that is not flowing. All right, and that brings us actually to our first point. The first point of the hydrostatic pressure and whatnot is the hydrostatic condition. What is the hydrostatic condition? The hydrostatic condition says this: a fluid at rest has no shear stress. All right, a couple of key things here. A fluid at rest. All right, what does this mean? It's not flowing. Okay, has no, literally this means zero. Okay, shear stress. What is a shear stress? Typically we say tau for shear stress. It is a force over area. In particular, if I have an area like this, all right, a shear stress is a force parallel to the area. A normal force is normal to the area, right? So typically we'd say tau and N, right? So this is a fluid at rest can have no shear stress, meaning a fluid at rest can have what? It can have a normal stress, right? And where does the normal stress come from? Typically it comes from pressure, okay? So a fluid at rest can have no shear stress, so a not moving fluid will have zero shear stress, but it will have normal stresses that come from what we call hydrostatic pressure, all right? So let's think about how we can figure out what the hydrostatic pressure is. All right, so we're just gonna draw a little line here because now we're moving on. All right, first let's draw a shape that's a triangle that looks like this. Now this is a three-dimensional solid with depth into the board or into the computer, depth of, let's say, delta L into board. All right, and over here, all right, we're going to draw a little frame of reference. So here we have I and J. Nope, wrong. Sorry. All right, J and I. All right, which means if it's a surface inside our fluid, we have a pressure here we call Px. All right, and we have a pressure here we're going to call Pn. We have a pressure here we call Py, all right? And then we have, and let me just, I'm going to write these pressures in blue, so the forces are all be in blue, all right? Py, all right, just doing this, okay. And we're also going to have, okay, a force of gravity because it's a volume, all right? So this is a volume inside our fluid. So we have, this is just a random arbitrary shape inside our fluid. Not arbitrary, I've picked it to be this. All right, now we have our delta L into the board, and this shape is also going to have delta Y, delta X, and we'll call this side delta S. All right, and it'll have some angle theta. All right, so if I say what's the sum of forces in the X direction, all right, what's that going to be? That's going to be Px, that's the pressure. Now, in order, Px, in order to turn that into a force, I'm going to say it's times delta Y times delta L, because that's the face it acts on. All right, and given the frame of reference, that's positive. All right, and then I'm going to say that is minus Pn, the normal pressure on that surface there. And that's going to be times delta S, delta L, all right, and times sine of theta because of angles. And we're going to say that this is equal to 0. All right, now, we can also look at this and say some other stuff. Well, we can say, for instance, that delta Y over delta S is equal to sine theta because of the SOHCAHTOA. All right, and so we can rewrite that the sum of forces in the x equals px times delta y delta L. Hold on. Try to stick with my colors here, gang. Px times delta y delta L minus Pn. And if we do the substitution, all right, from the SOHCAHTOA, we also have delta y delta L. That equals 0. And what we get is that Px must equal Pn. All right. That makes sense, right? So that there's the normal force there is equal to the pressure there. All right. So that's the y forces. All right. Now, or the x forces. Now, I'm just going to erase all this and move px equals pn to give myself some more room. All right. So we did all that, and we found that px equaled pn. Now, what about the sum of forces in the y direction? All right. Well, what do we got? We got py times delta x, or sorry, delta y delta L, all right, minus Pn times delta S delta L cosine theta minus what? Minus the volume of that triangle times the mass inside of it. And that is going to be, in this case, rho g times delta L times 1/2 delta x delta y, because it's a right triangle. Okay. Again, because of SOHCAHTOA, we can make some substitutions here. All right. And in fact, what we can end up saying is that this is equal to delta x delta L. All right. And if it's in force equilibrium, we can say this is 0. Okay. And if we go ahead and solve this a little bit, what we can say is that Py equals Pn plus 1/2 rho g delta y. All right. And then I'll just do the colors the right way. Pn, all right, like that, and delta y. Okay. So what is this telling us? There are a couple of things we learned from this example. All right. The first thing we learned, one, if my fluid's at rest, remember this was an at-rest fluid, then the pressure gradient in the x direction is 0. There is no change of pressure in the x direction. And if we'd done a three-dimensional solid here, we would have also, and done it slightly differently, we would have found that essentially in a plane there's no change of pressure. Okay? All right. Remember that we also said that there was no shear stress. So there's still no shear stress in our system. All right. The other important thing we learned is that dP dy in my example here, but more often it's dP dz, is not equal to 0, that there is a vertical change in pressure. All right. So that example shows there is this vertical change in pressure. All right. And we could do a slightly more complicated example that does something similar. And what it would do is if we look at a cube, all right, so that instead of that sort of 2D example, now we're going to do a 3D example. Okay. And we said that we had on our cube here that this was delta x, this was delta y. Instead of delta, we're going to call this dx, which means, yes, that's right, everybody, differentials, and that this is dz, all right? And then we said, okay, let's assume that we're thinking about what is the net force in a fluid, all right? And we said, well, over here we have our pressure, right, P. We know that the pressure is going to be P over here. Then over here, we could say it's going to be P plus the partial derivative dP dx. All right? And we could do the same thing. Say that this is PZ. Actually, this would be PZ. Well, no, that's not Z. Sorry, this is P plus dP dZ. So this is just P. And then we could say over here, let's see. Over here we have P, and on this face we have P plus dP dy. All right. So if we did this three-dimensional example, we'd say, well, what are the sum of forces in the x? All right. Well, it's P times dy dz minus P plus dP dx, and I did something I should have written in here, times dx. Why is it times dx? So this is my partial derivative, and that's the distance I've traveled. So this is the derivative, and this is the distance I traveled. Okay, and so all of these should have that. So this should have a dz, and this should have a dy. Notice the derivative has that, partial derivative has that curly d, and the differential distances have a straight d. All right, so coming back over here, times dp dx times dx times dy dz. All right, and if I say that this equals 0, then I would find that the differential force in the x direction is just going to equal dp dx times dx dy dz. All right, I'd find the same thing, all right, in all three directions. So I could say that dfy would end up being dp dy equal times dx dy dz, and dfz equals dp dz times dx dy dz. Now the big difference in this example so far is what? I haven't used any force of gravity. All right, so without gravity, all these are this, and if I'm in equilibrium, all these are 0, right? So at a point in a fluid, all right, all the pressure is identical. I could say that the dF due to pressure is simply what? It's actually minus. All right, these all had minuses in front of them. Excuse me. Look at the math, and you can see I'm wrong right here. Equals minus, equals minus, equals minus. The force due to pressure equals minus the gradient of P times dx dy dz. Now remember, the gradient is equal to d dx in the x direction plus d dy in the y direction plus d dz in the z direction. All right, so the force due to pressure is this formula here, the minus the gradient dx dy dz. So it's a force due, it's a gradient of the pressure. So forces on this body only exist if there is a gradient in the pressure without gravity. And without gravity, everything is 0. If I include gravity, then what happens? Everything, so this is without gravity. If I include gravity and assume equilibrium, I get this. dp dx equals 0. dp dy equals 0. And dp dz equals minus rho g. All right? And I can integrate that. All right? And if I integrate that, dp equals minus rho g dz, then I can get that p2, and I'll say let's integrate that from 1 to 2. Let's integrate this from 1 to 2. All right? Then if I integrate that, I get that P2 minus P1 equals minus rho g Z2 minus Z1. Okay, this is hydrostatic pressure. Now, the signs here don't matter. They do matter, but I'm going to tell you they don't matter. All right, so this is the pressure in a static fluid, and the reason the signs are written this way is because of the way we derived it. Basically, what you need to know is this. As I get deeper comma, pressure gets bigger. Okay, this is what you need to remember. All right, why do I write that? The reason the signs are what they are is because essentially we said this. We had a fluid, the positive in the z direction was this way, and gravity was negative. All right? And so if I had this being a surface down here, and this is my solid surface. By the way, these three lines mean a liquid surface. And I said that here z1 equaled 0, and here z2 equaled minus 10. All right, what would happen? All right, I would say that P2 minus P1 equals minus rho g, Z2 minus Z1, Z2 minus Z1. All right, so this would equal what? 10 rho g, P2 minus P1. And so P2 equals 10 rho g plus P1. Or P2 is bigger than P1 because it's deeper. Now what happens if I do the same problem, all right, but I make some changes, all right? Instead of doing it the way I just did it, all right, I do it this way. I say over here, this is K, this is 0, this is Z1 equals 0, this is Z2 equals 0, and this is still gravity, is still down this way. All right? P2 minus P1 equals minus rho g, 0, minus 10. Other way around, right? Oops. Yeah, no, that's fine. 0 minus 10. All right? So I get that P2 minus P1 equals, sorry, 10 minus 0 equals what? Minus 10 rho g. Which one of these is deeper? P1 is, right? So P1 equals P2 plus 10 rho g. Look, it's the same exact answers we had before, except we've just switched what's 1 and what's 2, and where k equals 0 and all that kind of stuff. But P1, which was our P2 from before, is deeper, and so the pressure is bigger. All right? This is the key detail. This is because gravity and k are oppositely aligned. If, and that's the way we derived it, if for some reason you were doing a problem and k was this way positive, aligned with gravity, you'd have a real problem. This wouldn't work out. So let me show you an example. Right now, we'll say that this is 0 and this is 10, so this is Z1 and this is Z2. Why won't this work? Because gravity's in the wrong direction, and so your problem assumes that gravity's in the other direction of the signs. Okay, so let's just do this. P2 minus P1 equals minus rho g. Z2 in this case is 10 minus 0. So P2 equals P1 plus 10 rho g. Sign error. This is a minus. All right. So that was my mistake. Sorry. So minus 10 rho g. Look, this says that the pressure at 2 is less than the pressure at 1. This was because gravity was positive. Okay, so in general, as long as k, right, over here is opposite of gravity, you can put it wherever you want. You can divide Z1 and Z2 however you want, and you'll get the right answer. Or you can just remember that delta P equals rho GH, and whichever one is lower should be the one that has the bigger pressure. Okay, and that's an important detail. So the other thing I want to stress about hydrostatic pressure is this idea. So we know now that pressure, right, so hydrostatic pressure goes up as you get deeper. Okay. The other important thing we've learned here is that pressure does not vary outside of height. Okay? Meaning, let's say I draw a lake. Well, let's say a reservoir, like that looks like this. I'm going to draw it in blue. Okay, and it's a crazy reservoir, such that there's some land, which I'm drawing in black here, around it. Okay, okay, and here's my little reservoir. All right, and it's filled with lovely water, and it's got two sort of lakes, and there's an island in the middle, and there's a little, trench underneath it. This can only exist in a 2D world, but stick with me. Now, the important thing is, right, we now know that if I'm here, right, and I go here, right, and this is 1 and this is 2, because of hydrostatic pressure, we know that P2 is greater than P1, and in fact that P2 minus P1 equals rho G Z2 minus Z1, right? We've got that all worked out. All right, sorry, minus rho G. Let me get that negative sign in there. Minus rho G Z21. Now, let's say I create 2 more points over here, 3 and 4, all right? And the thing about 3 and 4 is that they are at the same height as 1 and 2, okay? So, the thing is, P1 equals P3, and P2 equals P4, because I'm not changing height. As long as I'm in a continuous body of water, all right, that does not have any flow in it, important detail, all right, then if I am at the same height anywhere in that continuous body of water, the pressure in that continuous body of water is the same, all right, and that's an important thing, all right. So pressure is deeper as I go down, and in a continuous body of water that's hydrostatic, pressure at the same height is the same everywhere in that continuous body of water. All right? And then one last thing we need to talk about for pressure. All right? There's the 3 kinds of pressure. All right? There's absolute pressure, P abs, and that's exactly what it is. That's the absolute pressure. That is the absolute value of the pressure that I'm measuring. All right? There's gauge pressure. Okay. This equals the absolute pressure, and for most purposes, we'll just write P for the absolute pressure, P minus the atmospheric pressure. And there's vacuum pressure, which equals the atmospheric pressure minus the absolute pressure. Now, vacuum pressure and gauge pressure are always positive. The reason vacuum pressure is useful is it gives you a positive number if you're working with vacuum pressures. Here's the deal. When you're working with pressure, you can work with any one of these. You can work with gauge, you can work with absolute, you can work with vacuum. As long as all the pressures you are working with are gauge, absolute, and vacuum. So if you are doing a problem and it says, give me the gauge pressure, then you either have to work in absolute pressure and subtract atmospheric pressure at the end, or you turn everything into gauge pressure by subtracting atmospheric. All right? As long as all the pressures are the same, your problem will work out. But if you try and solve a problem and leave some pressures in absolute and some in gauge, then you're not going to get a good answer. So typically for us, we're never going to use vacuum pressures. They just don't come up in what we're doing. But we will use these two, okay? And all you need to remember is if I'm working in gauge, everything should be in gauge, and then if I need absolute, I add atmospheric at the end. And if I'm working in absolute, everything should be absolute, and if I need gauge, I'll subtract atmospheric at the end. All right? That's the basics of hydrostatic pressure.